Look at the sweeping arms of a spiral galaxy. Now look at the coiled shell of a nautilus. Across vastly different scales of space and time, nature repeats the exact same geometric shape. If you cut a nautilus shell open, you find an incredibly precise internal geometry. It's known as a logarithmic spiral, a continuous curve that gets wider by a fixed mathematical factor as it spins outward. For centuries, people have tried to crack the code behind this shape, and the most famous answer is the Fibonacci sequence. The math is simple. You start with 0 and 1, add them together to get 1. Then you add the last two numbers to get the next. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. Take those numbers, build a series of squares with matching side lengths, and they fit perfectly. Draw an arc through them, and you get the golden spiral. It's a beautiful mathematical model. But does this specific ratio actually act as a divine proportion, hard-coded into everything from your backyard to the cosmos? To find where this math actually governs biology, we have to look at the strange reproductive rules of the honeybee hive. A hive has a single queen who lays all the eggs. If an egg is fertilized, it hatches into a female, meaning it has two parents. But if an egg is unfertilized, it hatches into a male drone. He has a mother, but absolutely no father. This chart traces that anomaly. At the bottom, we start with one drone. He comes from a single queen with two parents. Follow this ancestry tree back. Under this strict rule, each generation expands in a familiar pattern. 1, 1, 2, 3, 5, 8, 13. The drone's family tree isn't following a mystical blueprint. The Fibonacci sequence here is the literal, unavoidable output of how honeybees reproduce. We see a similarly rigid mathematical rule in plant growth, specifically in a phenomenon called phyllotaxis. The classic example is the sunflower head. This image highlights the natural geometry of a sunflower head. Notice how the seeds form distinct, intersecting spirals, called peristiches, sweeping outward in opposite directions. These spirals aren't pre-programmed by DNA. This biomechanical model shows the patterns emerge from physical pressure. As new seeds sprout, they continuously expand, creating growth pressure pushing outward. Simultaneously, the flower's boundary exerts outside pressure, pushing back inward, trapping the growing seeds. Squeeze expanding spheres into a confined space, and they have to organize themselves. The most mathematically efficient way for physical spheres to pack together under these specific forces naturally defaults into Fibonacci spirals. The spirals on a sunflower are a physical record of Newtonian forces finding the path of least resistance. So, if physical constraints force seeds into a Fibonacci pattern, do those same constraints shape nautilus shells and spiral galaxies? Actually, they don't. Measure it against a true golden spiral. Nautilus shells do not match. Their chambers expand at different angles. Spiral galaxies fail too. Their pitch angles vary based on distance from the center, refusing to lock into a single fixed ratio. We love finding patterns, and sometimes our brains get a little too eager. We've taken a perfect mathematical myth and overlaid it onto a messy, highly variable reality. Even though a galaxy doesn't perfectly mirror a sunflower, they do belong to the same broad mathematical family of logarithmic spirals. Down on Earth, the Fibonacci sequence is an incredibly efficient problem-solving tool. It helps plants pack as many seeds into a tight space as physically possible, maximizing their chances of reproduction. Out in deep space, the universe plays with the same geometric rulebook, but it tweaks the variables to manage the massive forces of gravity, gas, and stars. Math is a dynamic, living language that describes how physical forces act on matter. It forms the structural link between the dirt in your backyard and the distant edge of the cosmos.